Good morning, everyone. Today we will talk about the conductors. We know that when we introduce charges to a conductor, this conductor will have those charges distributed at the surface of this conductor, while they try to be as far as possible from each other. They tend to distribute in a way such that they remain stationary. They become electrostatic charges, and at the equilibrium they won't move and they will stay in their location, which means that no electric forces are applied on them, which means that there is no electrical field inside this conductor. So in this case, as long as there is no electric field, there is no electric forces, and those charges are going to stay in their locations, not moving. So now we know that the electric field inside the conductor is zero, and in that sense, as long as this electric field is zero inside, those charges are not going to move. Those charges are excess charges that we added to the conductor. If we try to apply Gauss's law inside this conductor, where we have closed surfaces where we can apply Gauss's law, we know that Gauss's law states that any closed surface, if there is no enclosed charges in those surfaces, then the electric field would be zero. And we know that the electric field inside the conductor is zero, which means that applying Gauss's law, we can conclude that the charges inside this conductor are also zero. In that sense, electric field inside the conductor is zero, and also charges inside the conductor are also zero after applying a Gaussian surface inside this conductor. Now we have seen that charges are zero inside the conductor. Then we know that the electric field are also zero. Whatever the closed surface, whatever the Gaussian surface you take, arbitrary symmetrical closed surface, you will always get a zero electric field inside the conductor. Now let's look at the conductor when we have an external field applied on that conductor. In this case, the electric field will be disturbed, as we can see here in this figure, such that those electric fields are always going to come on this surface perpendicular with the 90 degrees angle, which means that this field is going through this conductor. However, now by attracting those negative charges to the top, positive charges to the bottom, the inductor itself tends to induce an electric field inside opposing the external field, and that's why we have zero electric field inside this conductor as well. This internal electric field opposes the external electric field due to the polarization that happened in this conductor, and as a result the electric field is zero inside this conductor. Always remember that electric field lines, they come perpendicular on the conductive surfaces. since the electric field inside the conductor is zero, and as a result of this, we have seen earlier that the electric potential equals to the minus integration of the electric field along the displacement vector. In this case, if we say that the electric field inside the conductor is zero, this means the potential difference will also be zero. What does this mean? This means that V2 minus V1 equals to 0, or V2 equals to V1, which means that the potential at the location 1 and the potential at the location 2, due to the electric field being 0, are also equal. So the electric potential difference is 0. However, the potential at V1 and the potential at V2, potential at V3, potential at V4, everywhere inside the conductor, in this case, those potentials, electric potentials, will be equal. This doesn't mean that they are 0. They can take whatever potential is given to them. Now let's look at applying Gauss's law on conductors. We have a spherical conductor. This spherical conductor is solid conductor, where we introduced charges, excess charges that equal to QC to this conductor. What's going to happen now? Those charges are going to be distributed everywhere on the surface, on the outer surface of this spherical conductor. Let's see how we can derive this electric field along the radial axis. At the beginning, we will draw this spherical conductor. That's a solid conductor, and then we will introduce charges to this conductor. Those charges are QC. Those charges will be distributed at the surface of the spherical conductor. As you can see here, they will be distributed on the surface such that they are as far as possible from each other, with a total charge of QC. Now we have here also, as you can see, the center of the charge, where we want to then draw the relationship between the electric field and the radial direction. Now this is the center of the spherical conductor with a radius of capital R. Then we need to basically pick or draw a Gaussian surface. Here, for this spherical conductor, we do have two important regions. Region number 1, which is inside the conductor, and region number 2, which is outside the conductor. So if we were asked to draw the electric field everywhere, this means that you have to include region 1 and region 2. Then we work on picking a Gaussian surface for region 1. We will be working first on region 1. So this is my Gaussian surface. This is a symmetrical, spherical type Gaussian surface. Now we will apply Gauss's law in order to derive the relationship between the electric field and my enclosed charges. We know that Gauss's law states that the closed surface integral of the electric field over the area of over the surface of this closed surface equals to the charges enclosed within this closed surface divided by epsilon naught. So here the vector E for the electric field equals to ER, which means this is the radial component. We know that for those coordinates at the center of the sphere, we know that the electric field is would be pointing in the radial direction. We take the radial components ER, R hat, and then dA is, which is the differential surface element, as a vector equals to dA R hat. Now taking the dot product between the E vector and dA vector will give me the following: ER R hat dot dA R hat in the same direction equals to Q enclosed divided by epsilon naught. And in this case R hat dot R hat is going to give me a scalar, and it will be the ER times dA, and this is equals to Q enclosed divided by epsilon naught. Then that would be the relationship. ER can go outside now because the electric field is uniform, equals to the integration of dA equals to Q enclosed divided by epsilon naught. So now the relationship became the magnitude of the electric field times the integration of this closed surface, which basically I'm expecting it to be the area of the sphere, which is 4 pi r squared equals to Q enclosed divided by epsilon naught. This is the relationship for the Gauss's law for this conductive sphere. Now at region number 1, as we will see now, if we take region number 1, this is my first region that I need to apply Gauss's law in. In region number 1, we have the variable r smaller than the r capital. We are within the spherical conductor, so the r goes from 0 to r capital for this region. Basically, this Gaussian surface, as you can see here, does not enclose any charge. So the charge enclosed within this Gaussian surface equals to 0. And that's why we're going to write Q enclosed equals to 0, which means that the electric field now equals 0 within this region. As simple as this. The closed surface does not enclose any charge, then the electric field would be 0. Now we can draw the electric field for that region between 0 and capital R. Then the electric field would be 0, as you can see here. Now we need to work on region number 2. In region number 2, we have R greater than R capital. So now we need to also use the same expression that we have derived earlier, ER times the the area of that Gaussian sphere, and then this equals to Q enclosed divided by epsilon naught. Now let's draw the Gaussian surface, the second Gaussian surface, which is for region number 2. As you can see, this is the Gaussian surface. It's also a spherical closed surface with a radius of small letter r. This is my variable. However, now if you look at this Gaussian surface, you can see now the Q enclosed here is not 0. The Q enclosed is QC. I am enclosing all the charges that are on the surface of this spherical conductor, and that's why it is QC divided by epsilon naught. Now the electric field ER is QC divided by 4 pi r squared epsilon naught, which is also equals to QC if I rearrange it such that I write the epsilon naught first, r squared, or ER equals 2. Now remember 1 over 4 pi epsilon naught is K, so it's KQC over R squared as a magnitude. As a vector now I can say that it is ER times the R hat, or the vector E equals to QC over 4 over K QC over R squared R hat. Okay, so this is the electric field now for the electric field for region number 2 as KQC over R squared R hat. Now let's draw this electric field. Now the electric field here for at R equals to R capital, the electric field is K QC over R capital squared R hat. This is the maximum value, which is right at the location where I enclosed the charges. So I will put it now as KQC over R squared, and this is the maximum, as I said, the maximum of the electric field, and then it will decay till it reaches 0 at infinity. So this is the electric field for the first case, which is a solid spherical conductor. Now we need to move to the second case, where in the second case, as you will see later on, we also still working with the spherical conductors. However, now for the second case we will be looking at a different topology, as we will show in the coming slide. Now this is sphere, conductive sphere. It's very important. You can see that this is exactly agrees with what we have said before. The electric field inside the conductor is 0. Only the electric field right after and then decays. Now this is what we have derived and drew earlier. Now let's look at the second case. The second case of spherical conductors are spherical conductors with cavities inside. So what you see here is a spherical conductor However, there is a cavity inside. This cavity is full of air. Now we need now to draw the electric field versus the radial the distance, radial direction. Let's draw the spherical conductor first, and then the cavity inside. The cavity is air. Here we need to verify that we're using the same notations, same parameters, variables. This is A for the radius for the cavity. This is R capital for the radius of the outer surface of the spherical conductor. Again, here in this case we will be using the derived expression from Gauss's law, but before doing this, let's first introduce our charges, the one that we introduced to the conductor. It's QC, total charges of a QC at the outer surface of the conductor. Then after we introduce the QC, you can see that those charges have distributed themselves such that they are as far as possible from each other, and that's why they are at the outer surface of the conductor. Then now I need to put my two axes, E versus R, where I need to draw my electric field versus the radial distance R. We'll put the two distinguished points as well, which are the point A and the point R. Then we need to write the expression that we have derived earlier. ER equals to, times the area of the closed surface of the spherical of the sphere, that is basically defined by the Gaussian surface, equals to Q enclosed divided by epsilon naught. So in this problem we have three regions. Number one is the cavity. As you can see, they're defined by those surfaces. Here I have the cavity, and then I have the conductive part of the sphere, and then the outside, number three. So let's start with number one. Region number one is where R is less than A. Here, let's first pick my Gaussian surface. My Gaussian surface again is a spherical surface with a radius of small letter r. This is for region number one. R is between 0 and A for that region. And now let's look at the Q enclosed. You will see that we are not enclosing any charges. That's why the Q enclosed is 0. And in this case, the electric field is 0 as well. So let's draw now this electric field. The electric field is 0 between 0 and A. Now we will do region number two. Region number two, my variable R is, we'll draw the second Gaussian surface, which is the Gaussian surface for region number two. It will be also a spherical surface and has the radius of small letter r. Then we'll put the range number two. This range goes from between A and capital R. such that, again, that's a spherical surface. This Gaussian surface is a spherical surface, and it varies between r between a and capital R. Now let's look at the Q enclosed. How much is the Q enclosed for that Gaussian surface? If you can see that it is 0. I have no charges enclosed within this Gaussian surface. That's why the Q enclosed is 0, and in this case the electric field would be 0 as well. So let's draw this part of the electric field. It is 0. This is between A and R. Now the last region is region number 3. In this region we have R greater than capital R. This is the region goes from R to infinity. Let's draw this Gaussian surface. You can see this Gaussian surface has to be now completely outside the spherical conductor, also the radius of small letter r. However, here if we put the expression for Gauss's law, I can see that my Q enclosed now is enclosing QC. So QC now is the charges that my Gaussian surface is enclosing. Now it's different than region number 1 and region number 2. It is QC in this case because my Gaussian surface is completely enclosing this QC charge. So ER times the area of that Gaussian sphere equals to QC divided by epsilon naught. Now I can rearrange this equation to find the vector for exactly as what we have done earlier. QC divided by 4 pi epsilon naught r squared r hat. Then this is the electric field. Then if I want to now calculate the electric field in the same format as KQC over r squared r hat, then this is the magnitude. This defines the maximum electric field, which is right at the point I am enclosing the charges QC. This is right at R small letter equals to R capital. Now let's draw the electric field. This is the maximum electric field, and then it will start decaying till it reaches 0 at infinity. If you look at this equation here, if you look at this expression, you can see that here we have the electric field at a distance r, basically as if we had the charges concentrated at the center of the sphere. It looks like the same as the point charge. Now the third case that we will be looking at is the same spherical conductor. However, I have here a pointed charge added at the center of this cavity. So now I am introducing two charges. I am introducing a point charge at the center of the spherical conductor and the QC also at the surface of the spherical conductor. So let's see now how we can derive the relationship and plot the electric field versus the radial distance. We'll draw first the spherical conductor that has the cavity, and then we will put the pointed charge right at the center of this spherical conductor. This is a Q. Also, make sure that the notations are the same. We're using the same notations. Then we have this positive QC that is introduced to the spherical conductor, and those charges now are distributing themselves at the outer surface of the spherical conductor. This is a QC. So I have introduced two charges to this spherical conductor: the pointed charge at the center and the QC at the on the surface of the spherical conductor. Then we'll draw the electric field axis, and the radial axis are we need to plot the electric field versus the radial distance. So we have here again three regions: region number 1, which is the cavity; region number 2, which is the conductor itself; and region number 3, which is outside the spherical conductor. Using Gauss's law again, which is the closed surface integral of the electric field over the Gaussian surface equals to the charge enclosed divided by epsilon naught. In this case, as you have seen earlier, the electric field will be ER times the area of the sphere, which is 4 pi r squared, equals to Q enclosed divided by epsilon naught. We need to evaluate the first region, region number 1. In this region, we have this is the radius of the cavity, which is, as you can see here, A, and then we have the radius for the outer surface of the spherical conductor, which is capital R. Now we need to draw our Gaussian surface for the region number 1. It will be this sphere with a small letter r as the radius. Now we are at region number 1, so this r varies between 0 and a, which means that the Q enclosed for this region is Q equals to Q. My Gaussian surface, this closed Gaussian surface, does indeed enclose a charge that is Q. So if I substitute now this Q enclosed with a Q in my expression that I have derived earlier, I can find that the electric field is Q divided by 4 pi epsilon naught r squared. This is the magnitude of the electric field for the region number 1. Now here, if I am to plot now this region, you can see that once r goes to 0, then theoretically electric field would be infinity. Theoretically, we will be coming from very high value of the electric field down to the value of the electric field right at r equals to a, which is my first point. So I'm coming now, I will be drawing the response for the electric field. It will be coming from very high value relatively, and then all the way down till I reaches the value for the electric field right at r equals to a. So I try at r equals to a, it will be Q 1 over 4 pi epsilon naught is K, so it will be K Q over A squared. This is the value of the electric field right at the A, at radius equals to A. Now the next step is the second region. Now for the second region there is a very important point that I would like to explain to you what's going to happen due to this pointed charge that we have put at the center of this spherical conductor. So this positive Q, this pointed charge that we have put at the center of that spherical conductor, is going to affect the charge distribution, as we will see. This pointed charge is going to polarize my spherical conductor such that it will attract the negative charges from this conductor closer to the closest point to the positive Q, and also will result into pushing the positive Q to the surface of the spherical conductor. So remember that the conductor itself is neutral. However, because of this point charge that I put at the center of the cavity, this pointed charge polarized this neutral conductor, forced the negative charges to come close to it, and pushed away the positive charges. Those positive charges went to the surface now because of the repulsive forces with the Q at the center of the spherical conductor. So what happened now? Now the conductor got polarized, the negative charges got distributed on the surface of the cavity, and the positive charges now went up and joined the charges that we had at the outer surface of the spherical conductor. So right at the surface now I have the summation of a QC plus a Q, and right on the surface of the cavity I have negative charges minus a Q. So where did those minus a Q and the plus Q came from? They came from the conductor itself. The conductor was a neutral. That's why if you add minus Q to plus Q, it will give you 0. But because of the point charge at the center of the spherical conductor, this conductor got polarized, negative charges were attracted, and they were distributed on the inner surface, which is the cavity surface, and the positive charges were repelled. They went joined the charges at the surface. Now we'll draw this Gaussian surface for region number 2, which is in the range between A and R capital. So now my region number 2, the R, my variable, is going to vary between the A and R capital. Again, we'll be using the same expression that we derived earlier from Gauss's law, equals to the Q enclosed. Now let's see what is the charge enclosed. It is the positive charge Q, the one that at the center of the cavity, minus a Q, right? Minus a Q divided by epsilon naught. So the total charge, the netted charge enclosed by my Gaussian surface number 2 is 0, which means the electric field is 0 within the conductor. Now this is exactly what we have talked about earlier in the lecture, that the electric field inside the conductor is always 0. Now we'll move to the third region. The third region, basically I need to draw my Gaussian surface. It will be completely outside the spherical conductor, region number 3, and has a radius r. However, this variable r, this radius r, now takes a range that is greater than capital R. So this goes from R and ends at the infinity. This is basically the range. Now here I need to calculate the Q enclosed. Now let's look at this figure. What do we have? I am completely enclosing the whole spherical conductor. So what do I have? I have the pointed charge, which is in red, plus Q. I have the negative charge minus Q, which are at the surface of the cavity. And then I have the charges at the surface of the outer surface of the spherical conductor, which are plus QC plus Q. So I kept the color the same. So now make it an now divided by epsilon naught. So Q will cancel with the Q, so I ended up with positive Q plus QC. So ER is Q plus QC divided by 4 pi r squared epsilon, and then ER is K Q plus QC divided by r squared. This is the magnitude of the electric field for region number 3, which is R greater than R capital. Now if I want to draw this field, I need first to define the value where basically at the border R small letter equals to R capital. So this is the value of the electric field, and then it decays till it reaches 0 at infinity. So the value at R is K times the summation of those two charges, Q plus QC divided by R squared, which is the R capital squared. That's the point at the border.